So for this question, I compress a spring, and then I let it go, and the block slides across a low friction surface and compresses the other spring and comes to a rest. I want to find this compression. I'm going to use an energy lens, because I have a transition with the spring potential energy that turns into kinetic energy. And nothing's lost, so it all turns back into the spring potential energy on the right instead on the left. I know that these two energies have to be equal. And so I can write 1/2 kx squared is equal to 1/2 kx squared, where this is left, and this is right and right. If the spring constants were the same, the compressions would be the same, but they're not. This spring constant is greater by a factor of 2. So that means this must be greater by a factor of 2. If this has a greater spring constant, this must have a greater compression. And so xr squared must equal 2 times xl squared, or xr is equal to the square root of 2 times xl. Let's check. You put a square root of 2 in there, you square it, you get a 2 out. That gives this number a 2 because this has twice the spring constant. And that's equal to about 1.4 times xl. Now we want to make an energy diagram for this. So I increase my potential energy only when I compress these springs. So in here, there's no change in energy, and so this is flat. We remember that a force on an object is the gradient of its energy, or the slope on the energy distance graph. And so this should be flat because there's no force acting in here. And on this side, we know that the energy is going to grow like x squared. So this should be parabolic. And there's going to be a parabola on the other side, but because the spring constant is twice as great, the energy of the compression must be twice as high. Let's say that we start this block with the spring compressed to about here. We'd say, oh, alright, this is the potential energy it has, but there's no kinetic energy when we start it. So this is the total energy, and I just write this across here. It's the total energy. Then when this guy's launched, that potential energy turns to kinetic energy, which is this much kinetic energy, and turns back into potential energy. And this spring compresses to here. So we can see this compression is less than this compression because this is a weaker spring. Then we change the scenario. What if we have friction and there's a coefficient of friction of 0.3? Then as this block slides along, there's going to be a frictional force. And we can look at this through two lenses. One is that friction will accelerate it in that direction. But two, that friction will also turn some of its energy, its kinetic energy, what was originally spring potential energy, it'll convert some of that energy to heat through the work of friction. So the final compression here is going to be less. So let's first find the acceleration. I have forces of friction and acceleration. I'm going to use a dynamics lens because I know that this force of friction causes acceleration. I immediately write the sum of the forces equal mass times acceleration, and I do a free body diagram where I have this mass, which is 2 kg. Yes, there are forces in the y direction, the normal force and the force of gravity, that cancel each other out because the acceleration in the vertical direction is 0. But there's a frictional force, and I know that the force of friction is equal to mu times n, which in this situation is equal to mu times mg because we're in equilibrium in the y direction. If I want, I can put that in to say that this is 0.3 times 2 kilograms times 10 meters per second squared, which is 6 newtons. But I want the acceleration. So this is the only force acting in this direction, so I have force of friction equals mass times acceleration, or the acceleration equals force of friction over the mass, which is going to be equal to 6 newtons divided by 2 kg, which is 3 meters per second squared. Then lastly, how do we find the compression if we have energy loss due to friction? And what we do is we take our original equation of spring potential energy on the left is equal to the spring potential energy on the right, plus the heat energy. Okay, and this is the work of friction. Now because we have some energy lost here, this number is going to be smaller and the compression will be less. We can quantify that if we want, just to say, yes, the spring potential energy on the left equals spring potential energy on the right, plus the force of friction times delta x. And I could substitute this in, because I've got it. But I could also recognize, I've already calculated this, it's 6 newtons times 2 meters. So this is just 12 joules. If I had the spring constants and the compression, I would just calculate this initial potential energy, I'd subtract off 12 joules from it, and I'd set it equal to 1/2 kx squared and solve for my final compression.